all here for astronomy on tap? Wonderful. We're just early. Yeah, oh yeah. I'm early too. Yeah, no, my office is cold. It's colder inside the office than out here. I didn't bring a jacket, so I just thought 4 p.m. Why not sit here instead of sit there? You usually come to these? I think we've been to three. Three of them. Okay. Do you remember? Remember the three? By chance, do you remember which three?
Yeah. I'll probably all this year.
Okay.
I don't know. Some of them are kind of the obvious.
Some folks are better. Some folks are worse, or making their work accessible. That's true all the way up. So the professors teaching the classes, it's sometimes
I get that most of the grad students are super busy.
yeah. No, it's totally volunteer run.
I'm trying to remember, I can almost remember what they were.
Yeah. Any about planets?
And this one of them was about
Any of them about stars? Galaxies?
some of them were little kind of text.
Yeah. No, they get. I think you went too far. Keep going. Yeah, keep going. Keep talking. No, I definitely don't. Test. 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 So it's showing up here.
Okay.
That's not going
So how
there.
close should I be?
I don't know what the situation is.
Is this like the only mic we got?
No, it's between this and there is the
Okay.
problem. I don't know why. Test. You tried this one as well, so stand somewhere like within the tent, but like over by the blue strap. And benchmark. I think I'll hear this on the stream, but won't. Do a big thing.
Well, thank you. Now,
Hold on.
stream plan. So still, we're still staying here.
So we're going to do 10 trivia questions. If you need a trivia sheet, please come up to Bing. They will hand them out, please. Sorry, we're a little short staffed today. We're going to hand out the trivia sheets and get your golf pencil. As a reminder, once you get your sheet, put an awesome team name that I can read. And it's fun. You can be in teams. You will all get prizes. Also, we're going to go through it one question at a time. You'll get a minute to look over the question and write an answer. And then we'll go through it again, and then you'll get a short time, and then we'll be done. So, we'll start in a second once you get your sheets. Okay, so we're going to get started. I think the light is good enough today that I don't have to read them out. So let's just go. You're going to get 1 minute, and then we'll go back around. Okay? Here we go. First question.
For galaxy quest. Numbered his objects, looked at his backward at the century into the first scene. So Messier 61 was first scene.
I didn't know that. Was he like scoping?
Was he what?
Was he scoping?
He was left-handed, so back in those days, he won the last one right, left-handed, so he was left-handed backwards. I was just in France.
Also, immediately when you're in France, just know all the things.
Yes.
Step on
It's plugged in. Let's feel it. People like, you know, go back and change the previous answers based on the psychology of what you must have been planning. The quiz master.
I modify my questioning, like, what stands out as an impression? Because it's really, even the image doesn't change.
Yeah. That's for the DVD player, so Finding Dory to turn on. That's a good exit plan. If you're not happy with the talk, then that's a good one.
I was worried. Where's the dog? I've always heard of the only
Oh. Well,
yes. I was solid. Nope, you are so close to the You're not trying to track me.
Well, how much will it
I know, sorry about that. I thought we were talking about like that much person.
No.
Do it, have to do it. Right? Yeah. Although the movement.
This is like, I said,
Always waiting for
Okay, that was the first round through. You did not get all of your questions, and it's okay. We're going to go back really quickly through all the questions. There you go.
Not even waiting to see them all a second time.
Okay, that is all the time we get. So, if you would like to be judged on your trivia to maybe win a prize, please come bring it up here to make a collect. I will grade them. So bring it on up here, and remember your golf pencils, please.
Are winning. So there will be people in people here. Where did it go?
All right, let's get this thing started. Are you ready for an awesome talk? Yes. Okay, so if you are regulars at Astronomy Talk, you might already know our amazing speaker, but if you don't, you're about to meet them. They're amazing. This is Binh Nguyen, who's going to give us an awesome talk. They're a second-year student at UW. They're currently working with Dr. Arianna Long, who is our newest faculty. We're super excited for her. Their research is searching for tiny neighbors in massive quenched galaxies, which we might learn about in today's talk. And they're also really awesome at writing. I can't wait to read their book when it comes out. And you can talk about that if you want. And also have trivia questions, so if you're stumped, plan them. But anyway, let's go.
Hello, hello, can you hear me? Can you hear me? Okay, sound check. Okay, wait. Jake, do I need like a thing to go to the sides?
Yes.
Okay, that's good. All right, so the title of my talk today, basically this whole evening is just me. So you're gonna have to stick with me even if you don't like me. Anyway, so my talk, the title of it is Ceci galaxy. Do you know what that refers to? Yeah, yeah, exactly. So in case you don't know, there's this painting by René Magritte, who's like some French guy, and he had a painting called "The Treachery of Images," and on the painting there's like a pipe, and the line below says like "Ceci n'est pas une pipe," which is like, this is not a pipe. So like, what the hell do you mean? And I'm trying to like evoke the same theme here. So the general topic of this is about galaxies. That's very broad, but it's about galaxies. It's basically a talk about the definition of galaxies and like, I don't know, how we came to our current definition and what challenges there are to the current definition, and basically just like a very theoretical talk. So I hope that's okay. I hope you're up for that. Anyway, so I have an outline, so this is not like a disorganized like rant. So first is, how do we get here? Like, how do we get to our current definition of galaxies? And then we're going to talk about some problematic galaxy-like objects, which I put in quotation marks. And yeah, it's self-explanatory. Anyway, so how did we get to our current definition of galaxies? like I'm glad that I got like full control of both the trivia quiz and the talk, so I could like engineer it in like a certain kind of way. So as you might have like figured out from the quiz, like the definition, like the word galaxy itself, it has a long history, and the history of the word galaxy itself starts with this thing. You might have seen it before. It's called the Milky Way. So the Milky Way, as you might have known, is the galaxy that we're a part of. And wait, do you see like 4 shadows, like 4 silhouettes here? Okay. Anyway, so I'm trying to like, this is like a transparent PNG file for like a human silhouette I found on Google. But anyway, the idea is that for all of history, like we have looked at this thing and we have given it like different names. And here are some names in English. There are, or like Europe, as like I'm just using different languages as like characteristic of like the whole region, which might not be true, but for English, we have 2 names. One is Milky Way. It came from like Latin, Greek, whatever. But basically, all many European cultures share this way of looking at the Milky Way as like a milky, like milky way. And then the second word used for it is galaxy, which is first attested in Chaucer. And anyway, and galaxy came from the Greek galaxios, which means milky. So basically, these 2 names just refer to the same thing, like, and come from the same like imaginariness, whatever. Anyway, we go a little bit down to the south in the in the Middle East, which I call like Swana, like Southwestern Asia and North Africa. It's called, I forgot how to pronounce this. It's basically like a path of straw. So the name for the Milky Way in Arabic is straw path because it resembles like when like a farmer drags like a car or something, like the straw or hay, whatever, just falls behind them like a path like that. And another name is Majara, which means like a lot or many. I don't know. I checked the dictionaries and all that. Like they're not too like sure about the etymology of this. Anyway, these 2 names are some of the names in Arabic for this thing over our heads. And then we go a little bit to the east in South Asia, like the galaxy becomes like the Milky Way becomes Akashganga, which means like the river in like the Ganges River in India. They see it as like that river in the sky. And then another name is Mandakini, which means slow flower, slow flowing thing. And you go a little bit more east to Vietnam or like East Asia in general. That's the name for it. Like then it has 2 names, Ngân Hà, which means silver river, and Thiên Hà, which means sky river. So what I'm trying to say is that at least like 4 regions of the world have like a variety of names for the thing over our heads. And it's like it's basically like the nature of humans. We like to have more than one name for something. And that's always been like the case with languages and beautiful things like the Milky Way. Now, something happened in like the 16th whatever century is that we started to actually get to look at these things like closely with telescopes, Galileo and all of those guys. And people start to see that like, okay, so when you look at that big whitish band thing, you also see like fuzzy things. And they call it like, and some of them look like spirals. Some of them look like, they just look fuzzy. And the spiral ones are particularly striking to the astronomers at the time. So they call them spiral nebula. And that name actually, is preserved from like the 17th century to like the 19th century onwards, whatever. So basically, there was a question earlier, like in the 18th century, people would call that thing, they wouldn't call it a galaxy, they would call it spiral nebula. Anyway, but we also have to mention that like there's also like the 19th century and then the 20th century, which is when Hubble and Edwin Hubble and others found that spiral nebulae like M31 are actually outside of the Milky Way. So they are distinct. Like people back in the day, like before Hubble, they thought that like, okay, yeah, they're just like, fuzzy parts of our own galaxy, our own universe. They literally think that like the Milky Way is all of the universe. But Hubble's like, well, those things are actually further away. So that means that, they're a different thing, that they're separate from the Milky Way. But at the same time, they look like the Milky Way. So how do we refer to these objects? How do we refer to Milky Way-like objects that are not in the Milky Way? So all of those languages have to adapt. So the names above become the official word, like scientific word for the Milky Way since the early 20th century. And then the names below, oh, crap. Anyway, they undergo some semantic broadening to start to refer to like things like Milky Way-like things. And now you know that galaxy is its own type of object, whereas Milky Way is one galaxy. So that's the same case with all of those ones. Sorry for the bad choice of color. Anyway, I thought it was going so well. So this is how the word started to the word galaxy started to change in meaning and start to refer to like a category of objects. But what this means is that the definition of galaxy began by visual comparisons to the Milky Way. Is this an issue? What's the vibe? What's the vibe? Say nodding or shaking your head? Okay. Okay, you're just gauging audience, I guess. Anyway, so whatever thought comes up in your head, just push it aside. I want to get back to that. Put a pin in that. Anyway, so from the early to the mid 20th century, galaxies are defined as like this milky, fuzzy things, whereas star clusters are grainy, like you see over there. I'm like, thank God the image looks nice this time. But anyway, galaxies are like their distances are further than they're basically outside of the Milky Way, and star clusters are within the Milky Way. And then we start to get, oh my God, look at that cat. Anyway, with better instruments, you could see far, like you could see like the cat. Oh, where's the cat? Anyway, but with better instruments, you could see more galaxies. You could start to see, like, compare the sizes and all that. So early to mid 20th century astronomers would say that like galaxies are big, star clusters are small. And by the end of the 20th century, the definition of galaxy was based on appearance, size, and distance with respect to the Milky Way. So it's not just like a visual comparison anymore. There's some distance involved, but it's still like, partly, it has the vibes of the Milky Way, therefore it's a galaxy. Anyway, but then, get it? Because it's dark matter. So, yeah, I hope you like that joke. In 1980, Vera Rubin and her collaborators, I guess, they never get mentioned, but that whole group, they found at least 21 spiral galaxies that are surrounded by dark matter. And what that means is that basically, there's this whole plot over here. I'm gonna go explain it. So basically, with Newtonian physics, you expect that like the farther you go from like the center of gravity, the more like the less force you feel, and like the slower everything should be. Okay, I don't have like, anyway, I'll just go over here. Yeah, this is a very long chord. Anyway, so basically what they found instead was that, because what they were expecting the the plot, like the rotation curve of the star velocities in these galaxies to like drop like that because, you know, gravity. But what Rubin and her collaborators found is that they actually go like that, like they kind of like flatten the closer, like the further they go to the edge of the galaxy. So they're like, there must be some mass holding back those stars, because like if they just go like spinning around like that, they're just gonna like fling, like, you know, get swung away. And the hidden mass is called dark matter. I can't recount how many times I've explained this, but I hope that you're familiar with that. But anyway, with later observations, we confirmed that, yeah, definitely, like other galaxies have that whole hidden mass situation going on, and they're called dark matter halos. And these halos are roughly spherical and extend to like 10 times the size of the galaxy disk. So like if you can see like the galaxy like the size of my, what is it called, remote? Yeah, if a galaxy is like the size of a remote, like the disk, then the halo, like the invisible one, is like big, like at least 10 times. You know, that's big. Anyway, so what does this mean for the definition of galaxies? Well, with SDSS, shout out to SDSS, I guess, we found some other galaxies that are like ultra faint because they're so faint and they're so small, therefore dwarf. And we found many of these galaxies around our own Milky Way, like Wilman 1. I just learned before this talk that Wilman 1 was named after a former astro grad here at UW. So representation. But anyway, these dwarf galaxies, their masses are like 10 to the 5th, like solar masses. And their half-life radius, basically like how much like the radius at which like half of the total light is emitted, is like 20 to 40 pc. I forgot how much that is in like light years, but very small, very small. And they are like almost entirely dark matter, and they can't like, you can literally count like the number of stars in them. I have worked with some UFD like ultra faint dwarf galaxy data, and some of them have like 50 stars. And yeah, this is like the rough estimate of like the average, like 100 stars. But compare those ones to the Milky Way, on the other hand, the Milky Way's mass is like 10 to the 12th solar masses. And the half-life radius is in kpc, so like thousands of times more than the little ones. And the Milky Way is like 90% dark matter dominated, which is still a lot, but much less than 99%. And yeah, I don't think you can count how many stars there are in the Milky Way. Like, I literally dare you. Yeah, that's a challenge. Anyway, so we found this new like category of galaxies, but their size is like very close to star clusters, because like that PC thing is like the size of like a big globular cluster. So what does that mean for the definition of galaxies? Anyway, so people start to use cosmological simulations, and they see that dark matter halos are like these like gravitationally bound regions within which like matter, ordinary matter, or baryonic matter, as they're called, fall into and form galaxies. So like there are these like like spherical whatever, and then matter falls into them and then forms galaxies. So like the presence of dark matter, to the consensus of astronomers right now, is like integral to the formation of galaxies. And within a massive dark matter halo, there can be subhalos, and these are where you can find like the dwarf galaxies that I just talked about earlier. So basically, all galaxies, big or small, have dark matter. And star clusters, they don't. So that, boo. Anyway, it's yeah, the Latin also makes it look bad, so boo twice. Anyway, with all of this, we arrive at our current definition of galaxies, which is that galaxies are gravitationally bound stellar systems that form and reside inside dark matter halos. Hey, Kat. Yeah, like the moment I talk about the current definition of galaxies, she comes here. It's like contesting that, I guess. Anyway, she'll like the next parts because spoiler alert. Actually, no, we're gonna talk about problematic galaxies. I put galaxies in quotation marks again. Anyway, so what do I mean by problematic galaxies? I don't mean like galaxies should be canceled. I mean like galaxies that essentially, like objects that essentially have galaxy-like features, but just don't subscribe to our definition of galaxies, the current one, this one. So first case, ultra compact dwarfs. They were discovered in 1999, and they were first called galaxy by these folks, and they're called ultra compact because they have the stellar mass of dwarf spheroidal galaxies, but the stars are very, very dense together. Like a dwarf spheroidal galaxy is like, I don't know, imagine like this much, and then an ultra compact dwarf has like the same amount of stars, but like condensed into the size of my remote. I know I've been using my remote as comparisons, but like, bear with me. But for these objects, they're mostly old stars, which are kind of like globular clusters. But that begs the question, like, okay, are these galaxies? Because like they have the same like stellar mass as known galaxies, but they're small and they're compact and they're mostly old stars like globular clusters. So are they galaxies or not? What the heck's going on? And there's no consensus yet. Like I still find some papers being like ultra compact dwarfs, not ultra compact dwarf galaxies. It's just like the fighting is in the in the terminology. But anyway, people who support the galaxy, like categorizing them as galaxies, would say that they are galaxies. And some people who oppose them would say that like, well, they're just big globular clusters, massive one, I mean. And then we have our second case, tidal dwarfs. They were predicted like from all the way back in the 50s by Zwicky, and I feel like this guy kind of like he predicts a lot of things. But they were discovered in the early 90s, and these tidal dwarfs are basically the result of interactions between massive galaxies, where tidal force is like a secondary effect of gravity, right? It's like pulling and sucking stuff. So when massive galaxies interact with each other, they would like come close together and they would pull on each other. And from those pulls, there'll be gas and dust from each galaxy like just kicked out into the neighborhood. And some of those would form their own galaxy-like objects. I have an example right here. Thankfully, the color is good, so I can show them. But anyway, so this is a galaxy being pulled apart. Can you see that? And the ones like S and W, whatever, the ones with like extra letters, are the tidal dwarfs that are forming as a consequence of this one big guy being pulled apart. And the same like this is the same thing, like one guy being pulled apart, and then there are galaxy-like things forming in the galactic tides, tails, whatever. So those are galaxy-like objects, and they're created in a very different kind of way than what we were talking earlier. Like we're saying that like matter falls into dark matter halos and whatnot, but these guys, they're like the results of like tidal interactions. And okay, this is the bigger question: do they have dark matter? Well, this is from so long ago, but basically, these folks, they compare the dynamical mass of these galaxies, like basically the mass that interacts with other stuff, to the visible mass and the stellar mass. And these values, the dynamical mass and the visible mass, are almost the same, which to these authors imply that these tidal dwarfs don't have dark matter. And they say that like this is the only galaxy-sized systems where this is the case. And let me remind you, this was written like 2001, like the year I was born. So like a lot must have. Oh my God, I'm sorry. I'm sorry. anyway, anyway, anyway. So anyway, I know that was a shock, but let's focus. Let's focus, shall we? We're here to talk about astronomy, not age. But anyway, so like a lot of things must, yeah, you know, there have been a lot of other works into tidal dwarfs and whatever, and I'm just pointing at like the original authors who first like proposed the idea or discovered or like the idea that like these objects they don't have dark matter, and since then like a lot of other works have been done on like other galaxy-like systems like this, and they're like, yeah, pretty weird, but still these tidal dwarfs, they got the size, the mass, and the luminosity of dwarf galaxies. So people are still like, well, sure, we're just gonna call them tidal dwarf galaxies. I mean, of course, there are some people who are like, no, just call them tidal dwarfs. And the reason why I say like tidal dwarfs versus like ultra compact dwarfs is to not like offend those people. Anyway, you think this is it? Yeah, there's more. There's always more. So this one, the cases I'm gonna talk about is more the case I'm gonna talk about. They're more like recent. So anyway, in 2018, like pre-COVID times, these authors found like this like ultra diffuse dwarf orbiting this one. You see this galaxy, right? Yeah. So these authors they found an ultra diffuse dwarf orbiting that big galaxy. And what do we mean by ultra diffuse? Well, ultra compact, ultra diffuse, they're polar opposites. Ultra diffuse means that they're very spread out. That's it. And the stars on the outskirts of this dwarf, which they call DF2, they have much smaller speed than in the inner regions, which kind of goes against what Vera Rubin already found like a few decades ago. And they also found that they also did some calculations to account for like the motions and whatnot, and they found that DF2 like has like 1/400th of the dark matter that you expected of a galaxy of that size. So they published an article on Nature, which is where most like I think every astronomer would go for like sensational like news, with the title "A Galaxy Lacking Dark Matter." And of course, when you say a galaxy lacking dark matter, that kind of like grinds some people's gears, you know? So there were pushbacks from the community. There were people who were like, I think they measured it wrong. I think because like there are some authors that I checked out and they were like, so those guys, Van Dockum or whatever, like they didn't measure the distance correctly because like the way they figure out the stellar mass and the brightness and all that relies on like a calculation where one of the factors is basically how distant do they think they are from this object. And the authors of this particular like response paper say that like they might have measured the distance wrong. Therefore, it complicates the later results and whatnot. But then an independent study by these two authors, they confirm the original author's distance measurements, and they say that yeah, we also measured that like DF2 doesn't have much dark matter, which is once again kind of crazy. And what makes it even more confusing, which is why I titled it like that, is that later they found like another ultra diffuse dwarf also lacking in dark matter and orbiting literally the same galaxy. And then or like I think a few months later, another group of authors was like, maybe what happened with the second one is that they saw some tidal interactions. Remember tides? They theorized that DF for the second one might have been tidally stripped of the dark matter, and it's also like losing stars now because they see like stars being sucked away out of that small DF or whatever. So yeah, I don't know. What this means is that these authors are saying that like the galaxies that are lacking in dark matter might be because of tidal interactions. So with all of this in mind, let's go back to our definition. We're saying that galaxies are gravitationally bound stellar systems that form and reside inside dark matter halos. Sure, but wait, hold on. Wait, oh my god, you can't even see them anymore. I chose the wrong color. Anyway, what if they don't have dark matter? What if they still have the size of, you know, the mass of galaxies, but not enough dark matter? What if they form like in a different way than typical galaxies? Or what if maybe they were galaxies in the past, but they got like most of their dark matter sucked out because of tidal interactions? Does that mean they're not galaxies anymore? So those are some of the questions that we'll be discussing. And we already discussed them, but like those are some of the questions that complicate the current definition of galaxies as you see right here. So yeah, I think this is a good point to like have a break, and we'll come back with some more stuff. All right. Oh. Oh. Yeah, okay.
Before you run off, if you would like to learn about your trivia answers, we're going to do that really quick and then I'll let you go get more beer. I need more cans. Okay, here we go. So trivia answers. Hopefully you already know some. 1. The first known use of the English word galaxy is done by Chaucer. So, think about this. Okay, 2. What did galaxy refer to at the time? Just the Milky Way. See? In the 16th century, people would call this a galaxy? No, they couldn't see it. So, sad. In the 18th century, people would call this a galaxy. They would call it differently. 5. In 1931, would people call this a galaxy? True. Yes, they finally have a good definition based off of what we learned. 6. How massive is this galaxy? About 10 to the 12 solar masses. How much of the Milky Way is massive in dark matter? You should know this. They mentioned it, 90%. 8. How massive is Wolman 1, an ultra-faint dwarf galaxy? 10 to the 5 solar masses. The globular cluster Omega Centauri has the same mass as Williams. What is the same mass? It's 10 to the 6 solar masses. Close. Okay, and the reason why Wilman 1 is a galaxy, but Omega Centauri is a star cluster, is that William 1 has dark matter and Omega Centauri does not. True, we just talked about that. So, y'all were really smart. We have so many people that got 8s that were so close. Like, there's like 7 of them. Hold up. So, drum rolls for first one in no particular order. We have the Halians. Yay! Good job, guys. Okay, and then we have just Luke. Good job, guys. We also have It's Just a Tribute. Okay, very good, very good. We also have Robin. Good job, Robin. And then I like this name, Smell
Hello, hello, friends, and gentlemen. Hey. So starting again, the time is up again. So wait for a second for it to settle. Did you know that like when like matter like falls to like happen somewhere, they also have to settle? So you're also settling into the kind of the galaxy. Anyway, so where we it's right here. But where we left off, we're talking about the current definition of galaxies and like sort of like holes in them, the different cases, and we see that these like this definition right here, there are some galaxy-like objects that don't fit this definition strictly. So our question right now is like, what the heck? And basically now let's talk about if it's possible to find a better, more like what is it, like more comprehensive. Thank you. Yeah, thank you. More comprehensive definition of galaxies. Oh, wait, what? Okay, so we define galaxies. Question mark. So let's think about it. Galaxies, right? What are two things a galaxy must have? Just raise your hands and I'll take that. Okay. You go back. I have two things. Yeah, you.
I think they should have stars and dark matter, and I also think they should either have a supermassive black hole.
That's 2.5? Anybody else? Sorry, what? Light from stars, but not stars. See? That is squeeze. Anyway, so it seems that we agree that there's gotta be some star, like whatever stuff there. So let's start with a working basic definition that like, two basic things that work for like all of our cases. Two basic criteria. I know why I made like this experiment. They have to be gravitationally bound together and then have stars. How are they gravitationally bound? Anyway, so these are two basic criteria that like there were some papers like arguing about like what other criteria should have, and then there are some Australian astronomers who were like, I forgot their names, sorry guys. They were like, hey, hold on guys, let's settle with this first and then we're gonna argue later. So that's why I put the criteria here. What other criteria? See? Now we're gonna get into like the more like convoluted stuff. So the first suggestion I should take this off. How does it work? Okay. A lot of engineering. Anyway, so the first suggestion for a criterion is that the two-body relaxation time must be longer than the age of the universe. What the hell does that mean? So you know stars move, right? You know they move, and they move in the system in the galactic system. And when they move through matter in space, they interact gravitationally with this matter, and that's called dynamical friction. And they're also called like aerodynamical drag, like how airplane would drag, And this matter it can be dark matter, it can be other stars that they meet on their way, and they kind of it makes them bounce off each other or whatever. And over time, a star interacts so much that it starts to lose memory of its original orbit. and its path will be more like randomized and will be determined by whatever comes its way, basically. So like that that whole thing where like a star usually like has its own like orbit and whatnot, but then over time it just loses memory of its original trajectory, and therefore like its path becomes more randomized and whatnot. That's called relaxation. And think about it this way: if a star, if every star in the system like starts to just lose memory of where they're going and just go out randomly, it'll be like a very chaotic system, you know? So this, like to ensure this doesn't happen, some of the astronomers suggest that a galaxy's two-body relaxation time must be longer than the age of the universe, aka it should take more time for a galaxy to for a star in a galaxy to to be basically to lose memory of its than the age of the universe. Because like if a galaxy's stars like their two-body relaxation time, this is a lot of jargon, but in that time it's longer, it's less than the age of the universe. It means that at the present we're gonna have systems that are just very randomly chaotic. I don't know if we'll want to be in a system like that. But anyway, on the right side is a what is it? A GIF of track dynamical friction. So you see how the star gets kind of like it goes into the sea of star matter and it has experiences of forces, whatever. So that's the first criterion that has been mentioned. The second one is complex cellular populations. See, most star clusters that we know, they only have one cellular population. They form on the same like molecular cloud and whatever, and they grow up together, that kind of stuff. However, if there is some leftover gas from the first era of star formation, and basically like if there's some extra gas from the first like seven nurseries, whatever, and that gas has like more metal because of supernova happening, then a second set of population of stars can be born in the same system. So like we can get like a second generation where there's like more metallicity in the star composition and whatnot. So that's what they mean by complex stellar populations, is that it should have the galaxy should have more than one generation. If that makes sense. But well, there are also massive globular clusters with complex populations, and this criterion would qualify them as galaxies. Once again, we got Omega Centauri over here. Like we had to like skirt around Omega Centauri so much to like find a way to define galaxies. This thing, it's obviously a globular cluster, but it just checks so many boxes. And speaking of checking boxes, let's do that. So, so I made like a mega table of objects and their galaxyhood based on some criteria. So, Milky Way, it's gravitationally bound? Yes. Has stars? Yes. Grammar halo? Yes. And similar in size, mass, luminosity to a known type of galaxy? Duh. And then the two-body relaxation time is not on the edge of the universe. Yes. Complex set of populations, of course. But then we go to alternate wolves. Are they gravitationally bound? Yes. Stars? Yeah, but not too much. But I'll take them. I'll take them off for that. I get the point for that. Partial credits. And do they have dark matter halos? Of course, they have so much dark matter here. But are they in mass and similar in mass to a known type of galaxy or group of galaxy? Well, not really. The reason why they're a known type of galaxy is because we call them galaxies. Like, it's kind of crazy. And then the two-body relaxation time, that checks out. And complex stellar populations. What complexity do you expect from like 50 stars? You know? And then we go to ultra-compact ghosts. They check all the boxes except for dark matter halos. And then tidal waves, same. And then those, whatever cases, whatever they qualify as, whatever. I remember I titled that like, excuse me, what? So like, I don't really know how to call them. But those ones, are they gravitationally bound? Yeah. Do they contain stars? Yeah. Do they have a dark matter halo? No. Or very, very insignificant. Are they similar in mass to whatever we know type of galaxy, dwarf galaxy? Yes. And we haven't had the calculations for these two criteria yet. And then what about massive globular clusters? Well, they check the boxes, the two boxes at first, and then they check the one. They check the box at the end. Sorry, I'm losing my train of thought here. And they don't qualify those according to those criteria. So what do we do with this? Like, there's even with the rigid criteria that we seem to agree on, there's always going to be some cases that just kind of fall outside of our, our range, whatever, our definition. So, what do we do with that? Well, we have to ask ourselves, what is the definition? See, this is where it gets fun. I mean, like, this is not a question in like astronomy specifically anymore. It's like it's something that you have to dig into like the philosophy of science to actually like grapple with. And I did. Anyway, so you got Trojan. Yeah, I'm the Achilles of your Hector. Anyway, no, I'm more like Odysseus. Because Odysseus was the guy who came up with this whole thing. Anyway, let's talk about natural kinds. Well, this is a very philosophy-heavy part, but scientists, they often try to classify objects or phenomena in the world around them so that they can reflect these like distinct, non-human, non-artificial aspects of the world. And what's non-artificial, non-human, natural. So that's why they're called natural kinds. And a few examples of that would be like gymnosperms. I don't know if I pronounced that right. Like,
You got it right.
that. Okay, thank you. And chemical elements are natural kinds, but edible vegetables, they're not a natural kind. And expensive cars are natural kind either. Are cars natural? I don't know. Anyway, think about it. Anyway, natural kinds. So this is what it means to be a natural kind. But how do we, what makes up a natural kind? How do we lump things together into a natural kind? This, see, philosophers of science have been arguing the hell out of this. So I'm going to present some of their views, and I'll use some examples from biology and chemistry and whatnot, because this kind of defined definitions has been more discussed in those areas. Anyway, the first view is essentialism, which is that members of a kind basically they have intrinsic properties, like properties that are independent of anything around them, and those properties would allow them the scientists to make inferences about all members of that kind. For example, chemical elements, right? Like a chemical element, like I don't know, give me one. Arsenic, thanks. They basically they have this many protons, and you can talk about different neutrons or whatever, but that would be isotopes. And the essentialists will be like, well, isotopes are also a natural kind, just like in a hierarchy of natural kinds. Like you got the elements, the chemical elements, and then isotopes and whatnot. So the characteristics of a chemical element, like their bonds, whatever, those are intrinsic properties, and they define what the whole natural kind of chemical elements is like. So for the essentialists, chemical elements would be a natural kind. But then we start to go into like different territories. Property clusters. It's a very complex topic, so I have capybaras there instead of species. But anyway, I hope you like the capybaras. But in this view, members of a kind they have properties that tend to cluster together that happen simultaneously with each other. Like you expect them to be together basically because of some underlying mechanisms. And these properties don't need to be like necessarily like intrinsic or extrinsic. They just occur together basically. That's why they call it property clusters. For example, species, something that some of us, many of us have been taught in like grade school is that a species like is a set of organisms that can't like that basically have like offspring that are fertile basically. That's the definition that many of us really use. But what about asexual reproduction? Because for organisms that asexually reproduce, I mean they just they reproduce by themselves and their offspring is also very fertile. So do they have to necessarily I don't know, like reproduce with each other? I'm trying not to go to I'm trying to be euphemistic here, like reproduction. But anyway, so a more recent broader definition is more with like phylogenetics, and with it's more like evolution based. And with mutation and recombination, it's hard to define a species based on common traits shared by them. So modern biologists instead they look at the evolutionary history of species members and what environment they live in, and basically like what properties of like a set of organisms would occur together. And with phylogenetics, they basically like draw like a circle around a set of organisms and be like, okay, this group has like these characteristics, and they're like the smallest possible set of organisms that comes from that shared ancestor, and that's a species. It's different from the reproduction-based definition, but that whole like circling the group thing is clustering them. So for the people who have this view, that would be like a natural kind. Anyway, the third one, when like the third one is like a punchline or whatever, like when you make jokes. This one is kind of a punchline, but it's very strange. It's called promiscuous realism. So I cite the name of the guy who defined it, who came up with the term in the first place, because I feel like you should look up a paper and read it. It's very, very interesting. But what Dupre, I think, advocates for is that entities inside a natural kind they might share properties and traits, but whether they belong to the same category or not, it's up to us to decide. Hence, promiscuous realism. An example of that is Lepidoptera, like the whole family of moths and butterflies. Basically, what are moths? Moths are members of that family that aren't butterflies. And there are some similarities between like different species of moth. Like they have like a cocoon, whereas the butterflies have like chrysalis. I forgot how they pronounce that. But some moths also have a chrysalis, whatever, like structure, and some moths are not nocturnal. So like for Dupre, that makes the category of moth and butterfly very like artificial. But he's like, yeah, that's cool because like what matters is not like a distinct like a demarcation between moths and butterflies. What matters is us. What do we want to do with the definition of moths and butterflies? Similarly, there's this whole like lily family here. Lilies, like the flowers. I've never seen them before. There are are flowers called lilies that are actually in the lily family. So for the lily family, people usually call them true lilies. But then there's been this whole debate, like, okay, how broad is this family and whatnot? And in this definition, the lily family would also have like onions and garlics. So how do we grapple with that? If scientists like agree one day that yes, the lily family should include onions and garlics, what does that mean for the florist? Think about it. So like, for debate, it's like basically obstacles. Like the scientists can be whatever, like they can be rigorous with their definition and be like, yeah, onions and garlics are lilies, whatever. But the florist doesn't have to abide by that, Like we can't sell an onion and be like, that's a lily, like no. So anyway, so that's what this means by that's what Dupre means by promiscuous realism. And that's a very strange name anyway. Thanks, Simpo. But see? Just I don't know. Anyway, Simpo aside, galaxies can be defined as a natural kind based on any of these perspectives. They got, interesting properties like gravitationally bound, they have stars, they have dark matter halos, they're, size, whatever. And then they also have properties that cluster together, like stars, the formation of stars, the gravitational binding, and the dark matter halo, they cluster together. So yes, you can define it that way. And then they've also got some properties like, body relaxation time and satellite galaxies, complex star populations and whatnot. So galaxies, in a way, will they will qualify as a natural kind, regardless of which perspective you take. But the question for us is, what the hell? Like how? Like, the question for us, how do we move from here? How do we go from here? Because how do we adopt a definition based on any of these views? Because each of these views, we're gonna exclude some things and we're gonna include some things. This is the same thing that happened with the definition of a planet. If you remember that, that was 2005. I remember that. But anyways, so the question of how to find things in science, I guess, is interesting. And there are some we can categorize the ways to define things like monism versus realism. Monism is that there's only one correct way to group things into natural kinds, and different natural kinds of the same things, essentialism basically, can be arranged into hierarchy, like elements, isotopes, whatever. And then pluralism is that we just use different definitions for different purposes. Like I said, biologists versus florists in terms of the lily family. So yeah, there are different ways of approaching the process of definition itself. And yeah, I honestly don't have my own definition of galaxies. I'm just here to stir some trouble. Yeah, I'm like the heiress to the Trojans. But anyway, in the future we have these, Rubin Observatory. We have some more SDSS updates. We have some new space telescopes. So we're expected to find some more galaxy-like objects. And then just settle on definition. Right now I'm working on these tiny neighbors around high direction, galaxies from the early universe, and they look very weird as well. And some of them, most of them are big enough to qualify, to have to qualify under the current definition. But what if we found a growth galaxy? Once again, another growth galaxy-like object that just throws a wrench into this whole thing. So anyway, that's my talk, and of course, as every astronomer does, I want to mention Rubin and whatever. So yeah, that means that I have passed the criterion of mentioning observatories So I am the astronomer. Thank you. Anyway, I'll take a break. Yes.
When you say stars have like a memory orbit, is that kind of like inertia? How does memory work in that context?
So the memory thing is just like imagery. So no, it's like I'm just trying to be like flowery with my
Okay.
yeah. Memory is like basically like you have the stars and they go on their orbits and they're basically loose like they lose track of their original orbits. So the way that I've seen many people explain is like they lose their memory because like stars usually follow like the similar path. Even though it's not the same path, it's like the similar type of thing. But with interactions, different interactions, they just deviate from that. And that's why they're not even the same path anymore. Does that make sense? Any questions? Any more questions? Yes?
How does dark matter stabilize into a halo after collapse?
That's a good question. So to answer that, I would have to point to like something called like.
Repeat the question.
Oh, sorry. So the question is that how does dark matter stabilize into a halo rather than collapse? So it has to do with like interactions between the dark matter and the dark matter inside the halo and baryon matter. And so there's something called the Vero theorem, which if you research galaxies, you have to use it so many times. It's annoying, but the Vero theorem says that like the I forgot the exact uh coefficient, but like basically the potential. There's a relation that like there's an equation between the potential and the sets of like the energy of a system of a closed system with the sum of the potential and the kinetic energy of that, and that allows the system to stabilize. And when we talk about even the radius of the galaxy in astronomy, when we say radius, it's the virial radius, the radius at which the system meets the criteria of virial theorem. If that makes sense. Okay, I will. Yes.
So I loved your lily analogy, and you could separate lilies into like florist lilies and like biologist lilies.
Yes.
Separate galaxies into like very, very galaxies, and then like maybe not galaxies. Who are the people who could like use that definition of maybe not galaxies versus the broader? Like, how would that be useful?
Yeah, so I would say that would have to do with different flavors of past research. Basically, like if you want like to categorize like that's the way I see it. The way you would categorize like a galaxy is like you have to have dark matter halos. That would be like the theorists, the people who run simulations, and you need to feed some some parameters to simulation and to create big galaxies, small galaxies. And I think they would adopt that rigid approach. But for the observers, I think they would be more likely because you can't really see dark matter, and like the observers, they would investigate these like galaxy-like objects, and they would be able to tell like the star formation history and the structure and the morphology of that, even without really caring that they did form inside dark matter halo. So like it's a question of like how much like theorists and observers agree with each other, because like a lot of these galaxy-like objects that confuse people are controversial because they, in some observational ways, look like galaxies. Like they have a mass and whatnot, but theoretically, like dark matter halo, they just don't have that. I hope that makes sense.
Yeah, totally. Thank you.
Thank you all for coming out and listening to an amazing talk. We'll be back in September. I want to say 26th, but I'll double check our social medias. And this is the last time we'll be up here. Our lovely Megan is coming back, our normal MC. So if you've been missing her, she's coming back. But thank you. Yeah, make sure you clear your glasses for Frank, and we'll see you next time. Oh, and if you want trivia, come up and see me. I have stickers for you.